Alrighty, good morning everybody. Welcome back to Math 105. Plan for today, we are going to start Standard 9, talk a little bit about mathematical proof writing. As far as upcoming things go, got my usual office hours on Monday, 10 in the morning and 2 in the afternoon. And as a reminder, don't forget that your Standard 8 quiz is due tonight. Any questions or comments before we get started today? Oh gosh, I forgot the joke today. Oh yeah. What is the best way to stay warm if you're in a cold room? If you're in a cold room, best way to stay warm is to go stand in a corner because it's always 90 degrees there. Okay, so for the last few classes, we've been, so for the semester so far, we've kind of been focusing on mathematical logic, being able to take statements, write them symbolically, being able to piece together logical arguments. And today's going to be a sort of turning point in the semester, and that today we're going to be transitioning into sort of the next major unit in the semester, which is sort of the idea of how do you actually prove mathematical statements just from individual axioms. In other words, given sort of these little pieces that we start with, how can we actually write and construct full mathematical proofs? Which is something that Standard 7 and 8 were focusing on. Standard 7 was about what makes a logical argument, being able to take something, break it down symbolically, relate it back to a law of logic. Standard 8 was focused on the idea of being able to be given these sorts of individual puzzle pieces and being able to combine them all in the proper order in order to be able to come to a logical conclusion. In the next several standards, we're going to be kind of using those skills to help actually construct mathematical arguments. And so Standard 9, we're not going to be looking at so much how can we put together logical building blocks so much, as Standard 9 is just going to be mainly focused on the discussion of how does one actually write a mathematical proof. Just given a single implication, what is the general structure? What does it look like to prove something like that? And so start off with, that we would start by just writing down a couple of definitions. Because in this packet, the main proofs that we're going to be focused on are going to be ones that involve even and odd numbers. So we're going to be talking about how to prove things like the sum of two even numbers is even. The sum of an even number and an odd number is odd. If you take an odd number and square it, you get back an odd number. Those are going to be kind of the things we look at in this packet. And these kind of arguments that the individual pieces are not so bad, but the difficulty, I think, is going to come from how do you structure your entire argument in general. To start with, let's do a couple definitions. Our first one is going to be a number A is even if A is equal to 2n for some natural number n. So in other words, we were talking about natural numbers. We're always going to be talking about numbers like 1, 2, 3, 4, 5, etc. You've probably seen lots of other numbers before in various math courses like 1.5 or pi or e. Numbers that can't be written, numbers that are not these counting numbers, but these are going to be the ones that we're really focusing on. So numbers even, if it can be written, A is even if A is equal to 2 times some other natural number. And we're going to say a number is odd. This will be another definition. Number A is odd if A is equal to 2n plus 1 for some natural number A. And one of the things we're going to do is to prove later on that every number has to be either even or odd. You can't have a number that is both. So as a quick example, if we were to look at the number 12, would you say that 12 is going to be an even or odd number based on your experience?
Even.
12 is even? What makes 12 an even number?
Because it can be divided by 2.
Yeah, 12 is a multiple of 2. There is some natural number that we can multiply by 2 that'll be equal to 12. So 12 is going to be even, since 12 is equal to 2 times, what can we multiply by 2 and get 12?
6.
Dr. Gersey promised us there's no number crunching in this class. I said there will be minimal number crunching in this class. I need to do just a little bit, just to build some definitions. Yeah, since 12 is equal to 2 times some other counting number, 6, that makes 12 an even number. Whereas 7, for instance, I will say is an odd, since I claim 7 is going to be 1 greater than some multiple of 2. We can find some number n such that 2 times that number n plus 1 will give us 7. So what can we fill in the blank here?
3.
It's going to be 3. Because we take 2 times 3 and then add 1 to it, that'll give us 7. And that's what it means for a number to be odd, is that it's equal to 2 times some other counting number plus 1. Any questions about our definitions of even or odd? So here's going to be our first claim in this package. I claim that if A is even and B is even, then A plus B must be even. So in other words, I'm going to make the claim that if we take 2 numbers of this form, 2 of these even numbers, and add them together, we'll always get back some other even number. Which, intuitively, I'm hoping is something that you've seen before. You take an even, you add it to another even, you get back a third even. So before we start trying to actually prove this, I thought it would be helpful to kind of take this statement and sort of break it down logically. Sort of like write it down symbolically and see what does it mean, what needs to happen in order for this statement to be a truth. So I'm going to split this statement up symbolically. I'm going to let this be my statement P, just A is an even number. My statement B is an even number, I'm going to refer to as Q. And then the statement A plus B must be even, I'll refer to as statement R. How can we write down this statement symbolically if we split it up like this? If P refers to A is even, Q refers to B is even, R refers to A plus B must be even, what would this statement look like symbolically?
In parentheses P and Q, with parentheses implies R.
Like that? Yeah, I like it. P and Q implies R. So ultimately, when I make this mathematical claim, this is what it boils down to. That if statement P and statement Q are both individually true, then statement R has to be true. So what would be our strategy that we could use for how we could actually show that this claim has to hold true? Well, if we look at the statement P and Q implies R, there's only one situation in which this statement can be false. What's the situation where P and Q implies R can be false?
If either P or Q is not true.
Well, I think if P and Q are not true, actually, then the statement would still hold true. Because then we would just have either a false implies true or a false implies false scenario, and the implication would still come out to true in those scenarios, if you recall.
If P and Q are true but R is false.
Yeah. The only time that an implication like this could come out to false is in the dreaded situation number 2, where our hypothesis is true, if P and Q are both true, in other words, but R evaluates to false. So I think our goal is going to be to show that that can't happen. We need to show that in every situation where P and Q evaluates to true, R must also evaluate to true. Because if we can show that if true implies false never happens, then that would tell us our implication is always going to evaluate to be true. So I think that's going to be our strategy. It's going to be to show that under all circumstances, where, can I record? Okay, can I record? I don't know why I'm worried about that mid-sentence. We're going to show that under all circumstances where P and Q is true, R must also be true. So we can't have a true implies false scenario. If P and Q evaluates to false, then it doesn't matter. If A is not even or B is not even, then our claim is automatically going to hold. So it doesn't matter if what happens if P and or Q are false. We only need to show that in the situation where P and Q is true, in other words, where P is true and Q is true, it has to be the case that R is true. Any questions about our strategy before we start writing the proof? Here we go. So that was kind of our general strategy, which I won't be writing out for every single one of these proofs. You don't necessarily have to either. I just kind of thought that since this is the first one of these that we're doing, it's kind of good to talk about what do we actually need to show. So here's going to be our proof. In other words, here's where we're going to make our logical claim, where we lay out the steps that show under all situations where P and Q evaluates to true, R is going to evaluate to true. So our first line of the proof is basically just going to be assume that P and Q is true. Because if P and Q is not true, we don't care what happens. So we're going to start by saying assume A is even and B is even. So in other words, we're assuming P and Q is true. And now we just need to show that under these assumptions, statement R must evaluate to true as well. What does it mean to say that A is an even number?
It's divisible by 2.
Yeah, A is divisible by 2. In other words, if A is an even number, then A has to be a multiple of 2. It has to be 2 times some other natural number n. Then A is going to be equal to 2n for some natural number n. And B is going to be equal to 2 times something for some natural number something. So A is even means A has to be equal to 2 times n for some natural number n. if b is even, then b has to be equal to 2 times something, or some natural number something. What would you all like to call our our something that b is equal to 2 times? We need a variable name for that.
X.
Call it 2x. You don't want to use n again?
Doesn't necessarily have to be n, because if it's n, then it's like the same. Then it could imply that it has to be the same number as a. People could get confused. I don't know.
No, I think you're absolutely onto something. We can't use the same variable name n again, because if we used n again and said a has to be equal to 2 times n and b has to be equal to 2 times the same thing n, then we're adding in an extra assumption that a and b had to be the same number to start with, because they're both equal to 2 times the same thing n. And we don't want to assume a and b are the same number to begin with. We're assuming a and b are both even, but there's lots of possibilities for even numbers. We could have a equals 2 and b equals 4, or a equals 6 and b equals 10 billion. We don't want to assume they're the same number, and so we don't want to use the same variable n a second time. So I totally forgot your choice here, but you said x, right? I'm on board with that. Does it make sense why we can't use n to refer to the same thing both times? So we know that a is equal to 2 times some natural number n, b is equal to 2x for some natural number x. And so now it would be something that would be very nice to have is that a plus b is equal to 2 times some natural number. Because if we can show that a plus b evaluates to 2 times some natural number, well, then a plus b would be even, and we would have that statement R is true. And that's what we're trying to show, is that under the assumption that p and q is true, that a is even and b is even, then statement R has to be true. In other words, a plus b has to be an even number. So, you know a is equal to 2n, and b is equal to 2x. What does that tell us about a plus b? Can we say anything about what a plus b must be equal to with what we know about a and b individually?
2x plus 2n.
Yeah, it's going to be 2x plus 2n. I'm going to say 2n plus 2x because we had this type of a term first. But since we can add things in either order, it wouldn't be wrong to say 2x plus 2n. Yeah, a is equal to 2n and b is equal to 2x. A plus b naturally has to be equal to 2 times n plus 2 times x. Our goal is to show that a plus b has to be a multiple of 2. Do we know that this thing, 2n plus 2x, has to be a multiple of 2? Why do we know that that has to be a multiple of 2?
We can factor it to 2 times the quantity n plus x.
Yeah, we know 2n plus 2x, using a property called the distributive property. We know we can factor out a 2 from that and write that in the form 2 times the quantity n plus x. So in other words, a plus b is equal to 2 times n plus x. Well, is n plus x a natural number? Because if it is, then we're done. We've shown a plus b is 2 times the natural number. And I think it is because n and x were natural numbers to start with. So when we add them together, we should get another natural number. Thus, a plus b is a multiple of 2. It's 2 times the quantity n plus x. Hence, a plus b is even. By definition, We've shown it's a multiple of 2, it's even. And our proof is done. Because what we've shown is that under the circumstances where statement P and Q is true, we've shown statement R has to be true. If either P is false or Q is false, then our implication isn't making any sort of promise. It's not making any sort of claim when A is not even or B is not even. So being able to so we only need to be able to show something in the case that A and B are both even. And we're done. We've shown that anytime you take two even numbers and add them together, we're going to get back an even number. Any questions about what we did here? Okay, let's try another one. Ultimately, I'm going to be asking you all to be able to write these sorts of proofs. Not going to make you do that right away. First, I kind of just want you to see some examples so you can get a general sense of what do you need to do when you're writing these sorts of logical arguments. But ultimately, this is going to come down to you all once we get to some of the double-digit standards in a few weeks. What's my next claim? A is even, B is odd. So our next claim is going to be that if A is even and B is odd, then A plus B is odd. A very similar sort of claim to what we saw on the front page, where we're saying if two different things happen, A is even and B is odd, I'll call those my P and Q here, then we want to show that A plus B has to come out to be an odd number. So if A is a multiple of 2 and B is one more than a multiple of 2, we want to show A plus B has to be one more than a multiple of 2. Same sort of statement. We're showing A and B, or not A and B. P and Q has to imply statement R. So once again, our strategy is going to be the same as our strategy from the front page. We're just going to need to show that under all circumstances where P and Q evaluates to true, R has to evaluate to true. If P and Q evaluates to false, then we don't need to show anything. Then our implication isn't telling us anything about what has to happen. But we just need to show we can't be in the situation where P and Q is true, but R is false. So let's start off in the same way. Our first line, just like before, is we're going to assume that the statement P and Q evaluates to true. It's going to be our first line in the proof. So how can we write that out in words if we want to start our proof off with the claim that P and Q evaluates to true? Anyone else want to give this a go?
Assume A equals 2n for some natural number and B equals 2x plus 1 for some natural number.
Okay, so you want to go right to what the definitions are saying. I was just going to write out assume A is even and B is odd, and then
That works too.
I was going to say, and then I think what you said would be a great maybe second line of the proof. After so right now I just want to say assume P and Q, assume A is even and B is odd. But yes, that's absolutely right. So if we write that out, we get assume A is even and B is odd. And then we can say it has to be true that A is equal to 2n for some natural number n. And b is equal to, you want to use 2x plus 1?
That's what I do.
Works for me. And b is equal to 2x plus 1 for some natural number x. Here again, just kind of plugging in our definitions for what it means for a to be even and for b to be odd. And just like before, if a is even, a is equal to 2n, b is odd. We don't want to use the same n again because the n here doesn't have to, the variable here doesn't have to be the same as the variable here. We just know b has to be equal to 2 times something plus 1, and that something doesn't have to be the same something in the equation a equals 2n. So a is equal to 2n, b is equal to 2x plus 1. So what does that tell us about a plus b? Let's get someone from this this column here. If a is equal to 2 times n, and if b is equal to 2x plus 1, what must a plus b be equal to? If we were to combine it.
2n plus 2x plus 1.
Yeah, just 2n plus 2x plus 1. We're just adding our two expressions together. If a is equal to one thing and b is equal to the other thing, then a plus b has to be equal to the sum of those two things. So our goal, something to keep in mind, our goal is going to be to show that a plus b has to be an odd number. So we'd like to be able to show that a plus b has to be equal to 2 times something plus 1. We want to show a plus b is 1 greater than a multiple of 2. Over here, when we showed a plus b had to be even, we factored out a 2 and showed that a plus b has to be equal to 2 times the expression n plus x. Is there anything we could do here? Any way that we could try and factor maybe part of this expression that'll show us we have 2 times some natural number plus 1?
2 parentheses n plus x parentheses plus 1.
Like that?
Yep.
I like it. Because lo and behold, if our natural number is just n plus x, if we call that thing, then a plus b has to be equal to 2 times thing plus 1, which is precisely what we need in order for a plus b to be an odd number. Running out of space here, so I'll erase some of this. Then a plus b is equal to 2 times n plus x plus 1 plus a plus b must be odd since it is 1 greater than a multiple of 2. It's equal to 2 times the quantity n plus x plus 1, and that's all we need in order for a plus b to be an odd number, is a plus b has to be equal to 2 times some counting number plus 1. And there's our proof. Similar to before, under all circumstances where p and q evaluates to true, meaning if we're operating under circumstances where a is even and b is odd, a plus b must come out to an odd number. And we've just shown that anytime you add, because a and b could, the cool thing about this claim is that since A and B could be any even and any odd number, this kind of works. You can plug in whatever you want for A and B. And we've just shown 1 plus 4 has to be odd. We've shown 10 plus 11 has to be odd. No matter what you plug in for A, as long as it's even, and no matter what you plug in for B, as long as it's odd, A plus B must come out to some odd number. Any questions or comments? Okay, now it's your turn. So what I'd like for you all to do is to take a couple minutes and see if you can see what you can make of this claim at the bottom of the second page. Or I claim that if A is even, then A squared must be even. If you remember, A squared is just going to be equal to A times itself. So I'd like for you all to take just a couple minutes and see if you could sketch out what might a proof look like for this claim.
May I go get a tissue from there?
Absolutely. Hello, students who are watching this online. I encourage you to try this out as well before skipping ahead in the video. Because as always, I think trying to do this yourself and then maybe seeing what the answer might look like will be a lot more valuable to you than just skipping and seeing what the answer is without putting any thought into it yourself. Keep going, students online, you're doing great. Students in person, you're doing great too. Keep going. And if you have any questions or want to ask me about something, like maybe it's a little help getting started, be happy to feel free to flag me down. If you feel like you finished, something I encourage you to do is try plugging in a number for A in your proof and see if your proof works for a specific number, like A equals 4 or 10. Okay, so now that you've all had a chance to think about this for a few minutes, let's actually go through and see what you all came up with. So our claim is that if a is an even number, then a squared must also be even. What could we write for our first line of our proof? We wanted to just start off by writing what are we going to assume is true, followed by then we'll go through and logically prove something else has to be true.
We have to assume that A is even.
Yeah, I think that's a good place to start. We're just going to assume A is even. So this proof, claim is actually a little bit simpler than our previous two claims in that we only have two base statements. Our statement P is going to be A is even. Our statement Q is going to be A squared is even. And then if we're proving something of the form P implies Q, then all that we need to do is we need to assume that statement P is true, and then show that in every situation statement P is true, statement Q also has to hold true. In other words, we can't have a situation where P is true, but Q is false. So assume A is even. What could we write out next after we assume that A is an even number?
A equals 2n.
Yeah, then A is equal to 2n for some natural number n. So that's just by definition of A being even. Since we don't have a B in this one, we don't have to use, I don't think we necessarily need the variable x appearing anywhere. Just because we don't have a B showing up in our claim. So I don't think we need to bring it in. So A is even, and A has to be equal to 2 times n. Where can we go from there?
Then A squared equals 2n times 2n.
Yeah, then we can go and make the claim that says if we know what A is, we should be able to write out exactly what A squared has to be equal to. If A is equal to 2 times n, then A squared should be equal to, well, the expression 2n quantity squared, which is equal to 2n times 2n. What do we get if we multiply out 2n times 2n?
4n squared.
Yeah, it's going to simplify to give us 4 times n squared. Don't forget, when you're squaring 2n, you need to square both the 2 and the n. So it's not 2n squared, but 4n squared. And what are we trying to do with A squared? We're trying to show statement Q has to be true. In other words, that A squared has to be an even number. So if we want to show that A squared has to be even, what do we need to do with this expression, 4n squared?
Divided by 2.
Yeah, we need to show it's a multiple of 2. So if we tried to factor out a factor of 2, what would we be left with here?
2n squared.
Yeah, that's exactly right. We could show that A squared has to be equal to 2 times this other counting number, just 2n squared. So A squared has to be equal to 2 times 2n squared. And then how can we write a line that'll finish off our proof for us? If A squared is equal to 2 times this expression 2n squared, what can we write as means of conclusion?
Thus, A squared is an even number. Must be an even number since 2 times any natural number is an even number.
Yeah. Thus, A squared has to be even because it's equal to 2 times some other natural number, 2n squared. Thus, A squared is even since a squared is a multiple of 2. There's our proof. Nice job. Y'all did a good job. Y'all did a good job of writing down this proof line by line. So one thing I want to point out in looking at this proof, and all three of the proofs that we've done so far, is that in order to show that P implies Q, we kind of went through several extra steps. So if our P was of the form A is even, and if our Q is of the form A squared is even, we didn't just, our logical argument wasn't just saying P is true, therefore Q has to be true right away. We didn't just go right from P is true to Q is true. We had several steps that we did along the way. I would say our argument looks something like this. We had a P implies Q, we had a Q implies R, or not Q, sorry. We had a P implies R, where R was the statement A is equal to 2n for some natural number n. So P, we first really just, our proof made the claim that P implied R. We then had a claim that R implied some other statement S, which was, S is going to be the statement A squared is equal to 2 times 2n squared. We kind of showed that if statement R is true, our statement S had to be true. And then from there, we showed that statement S then had to imply statement Q. If A squared is equal to 2 times 2n squared, well then A squared had to be even. And so our proof ended up being a sort of string of implications, just like the ones we saw back in Standard 8. The difference was in Standard 8, we were sort of given the P, R, and S and asked to find the Q. We were sort of asked to find we were given all the pieces and asked how can we string them together to make a single implication. Here, we're sort of taking the opposite approach to that. We know what our P is, and we know what our Q is, and we're just trying to find the steps along the way that lead us to sort of one big implication that'll take us from P to Q via going through a few steps in the middle. So here we're really using this transitivity property of the implication, which we saw back in Standard 6, to say if P implies R, and if R implies S, and if S implies Q, then P has to imply Q as well. So ultimately, our arguments are boiling down to the same sorts of arguments we were coming up with in Standard 8. It's just that this time, we're the ones who have to come up with these statements in the middle, the R and the S, etc., that'll get us from starting at statement P and ending at statement Q. Starting with A is even and ending up with A squared is even. And so that's why I spent so long in Standard 7 and 8 kind of putting together these logical arguments, is because when we're writing proofs like this, that's exactly what the same sort of thing we're going to be doing, is putting together these chains of logical implications like this. Any questions or comments? I'm going to let you go a few minutes early today. So I don't feel like starting the next page quite yet. So when we come back on Monday, we're going to talk about how we can use some of the other tools we've developed in order to help us prove things. Namely, how can we use the contrapositive of a statement to help us write mathematical proofs? So hope you all have a good weekend, and I will see you all on Monday. Video people, see you all eventually, I hope. You're all great.